directly into the open discussion. The open discussion is cumulative, so any questions you want to ask about this talks or anything before. Good, we continue now with Sudeepa.
Thank you, Wolfgang. So one of the goals of this workshop is to draw connections between theory, application, and systems. And we have heard more theoretical talks in the last yesterday and today. I am going to tell you about an application, and we will hear other talks in the rest of the workshop. So this talk is about an application of first-order logic to database education. So quick poll. How many of you have ever taught a database course or have been a TA of a database course? Oh, wow. Okay. So then you know that CS enrollment is increasing. So these are some statistics from Duke Computer Science. And so is the enrollment in database courses. Like we added some prerequisite, it dropped a little, and then it again went up to more than 300 from just 50 students 10 years ago. So how do we provide students or TAs automated personalized help to debug queries? Okay. Here is an example. This is a database that many of you are familiar with. This is the beers database. We have drinkers frequent bars, drinker likes beer, and bar serves beer. We don't really need this database in this talk. So suppose you as an instructor have given this question that find the bar serving a beer at the highest price. But the student returns that not at the lowest price. So your query is non-monotone, it requires a minus, student query is monotone. Now, how do you convince the student as a TA or as an instructor that where their query went wrong? And these queries, both the questions and the answers can get quite complicated. So this is a slide from Dan's lecture notes. And you can see that find drinkers that frequent only bars that serve some beer they like, only some flipped, and so on. And if you find your name here, that doesn't mean anything, okay? Okay, so these queries get complicated. So the broad goal of this project that we have been working on for a while is to build tools to help students debug queries, okay, without revealing the solution, of course. So how about an autograder? So like GradeScope, we do use autograder. So we have like a very carefully crafted database that my colleague Jun Young has built for several years. So you have the correct query and you have a wrong query. And then this is a test database instance. And the autograder checks if these two queries are the same on this particular database. Okay, so this is not query equivalence. Now, that is okay, but not quite, because the test instance can be very big and it doesn't pinpoint the source of error in student's query. Then we had a prior work. This is just to motivate our solution here, that we have this big database instance that differentiates the correct query and the wrong query. How do we find the smallest sub-instance that would still differentiate these two queries? Now you can perhaps quickly see that this is easy if Q2 is monotone, but it is NP hard in general. You can show that. And what we did here, that we used Boolean how provenance that we have been discussing in this program and also in this workshop, that to find the difference between the answer of Q1 and Q2, and then we are trying to find a solution that would make this Boolean how provenance true with minimum number of ones. So of course this is NP hard, so we are using SMT solvers and multiple optimizations. We have extension to aggregates. So this is this was like, that was the technical contribution. contribution to database education is that Zhengjie built a tool with a UI, and this has been used for the last 5 years at Duke by more than 1,600 students now, because we keep track of how many students for our NSF reports. So this has been a very highly useful tool for debugging relational algebra queries. And as you can see, like for this highest versus non-lowest, it returns a concrete ground instance showing three distinct values. And if these three values are present, then highest is going to return only one answer, but not lowest is going to return two answers. So this shows the difference. And we had a very detailed user study in the class in fall 2017, and then students were, we can skip this now, but if you quickly read this, you can see that the students were mostly very supportive and optimistic and about this tool, but they also pointed out some drawbacks, like it would have been very nice if it had more instances, because one instance is not enough to find all the edits, and add a little more context, like where did I go wrong, and so on. So these are these were the feedback from the students. So that motivated our next work, that can we specify the source of error using an abstraction instead of a concrete or ground instance. Okay, so this is the work that I am going to talk about in the rest of the time, and this is a joint work with Amir Gilad, who is now at Hebrew University of Jerusalem, Zhengjie Miao, now at Simon Fraser University, and my colleague at Duke, Junia. Okay, so here are our two queries. So this is the question again, little modified, that for each beer liked by drinker whose first name is Eve, so you can see in the correct query there is a little space there, find the bar serving the beer at the highest price. Okay, so this is the correct query, and the wrong query, it returns the non-lowest, and it makes another mistake, like it misses the space here. This is a ground instance. Yes.
When you say correct query or wrong query, you mean the semantics of the set of data that they give back, or because not efficient how it's written?
Not correct wise, semantic wise, not efficiency wise. We are not looking at like it can be arbitrarily complex. So this is a solution written by our previous work, that it would show a concrete ground instance showing three distinct prices. But where did this go wrong? That we want to show something like this, that Q2 returns the bar serving the beer at the price in the middle if there are three bars with different prices. Okay? So we want a condition like that. And we also want to find out all the errors, like first name is Eve, Q2 also returns wrong result if the drinker's first name starts with Eve but is not exactly Eve. Now, how do we do that? How do we get such abstraction as a solution? So this is what we proposed. This is inspired by C-tables. This is like a slight modification of C-tables proposed by Emeliansky and Lipsky for incomplete databases. This is a conditional instance. So instead of actual values, what we have here are variables like x1, b1, and so on. If something does not matter, there we have star, and we have a global condition here. So the global condition here says that if there are these three distinct prices, then this conditional instance will differentiate the correct query and the wrong query. Note that we do not have we are not starting with a database now, like we are differentiating two queries. Okay. And then not just one instance, we want to return a set of conditional instances. This is another conditional instance that is showing that if you return a name that starts with Eve but is not exactly like first name is not Eve, then also your query will go wrong. If you have a database instance like that. So how do we get such conditional instance? What we are doing, we are not directly working with SQL, we are converting that to domain relational calculus. And this is a query tree of this particular wrong query. when we have two queries, one correct query and one wrong query, we are looking at the difference of Q2 minus Q1, that is Q2 and not Q1. Okay, you could do the other way too. So this is the query tree for Q2 minus Q1. Okay. Now, for Q2 minus Q1, or in general for any Q, we want to characterize different ways Q is satisfied. That is, it returns non-empty results. So what are the applications? Of course, like you can use it in a classroom. You can explain why queries are different. You can explore how various parts of the query can be triggered by different data. You can use it to build your test suite, like the to construct that test instance to use in your autograder. So what is a good characterization for Q? What solution do we want? We want the basic requirements, that is the global, we want that for each conditional instance that we are returning, it should be consistent, that is the global condition should be satisfiable in that conditional instance. It should be sound, that is the query should be satisfiable by that conditional instance. And of course, minimality, like we don't want redundant tuples or redundant condition in the solution. Moreover, we ideally want completeness. Now, what does completeness mean? So you can one obvious notion of completeness would be take any ground instance that satisfies the query, and there should be a mapping, a homomorphism from your conditional instance to that ground instance, which does not work because there could be unbounded size for all these ground instances. So we are using a notion of coverage to define our completeness. Defining completeness was quite non-trivial in this work, and no redundancy, that we want to return a set such that like no one can be removed from that set. So how do we get to this solution? We are enumerating homomorphisms from query variable to label null in the C instance. Let's see a quick example for the soundness, that these are the free variables, these are the query tree, and then we are looking at all this different mapping, and then eventually what we are getting that this query tree, this conditional instance does not satisfy this query tree, but for another mapping this is now satisfied, so this could be a solution. Okay, I will walk through a very short example later. How about the completeness? The notion of completeness was motivated by code coverage, that we want to know that this different part, this does not mean anything for our work, but we want to make sure that this different part of this conjunction and disjunction, they are covered by these different conditional instances that we are returning. So this is the notion that we are checking whether a conditional instance would cover all these ground atoms of our query tree. So this conditional instance covers many of these except two. So this is one of our solution, and then if we add another one, then some of the remaining ones are also covered. So we want a set of conditional instances that would cover all our leaves. So this is finally our problem definition, that given domain relational calculus query Q, find a set of conditional instances such that these instances are sound, they are minimal, not redundant, and also complete, ideally. Okay, this is ideally. Now, probably so far, like you have already figured out that this problem is undecidable, because this is even existence of this solution is undecidable for general DRC queries, because from finite model satisfiability of first order logic, Krakenbrod's theorem. So we cannot get an exact solution to this problem, but that does not mean that we can get a heuristic. So what we are doing, we are running a chase-inspired procedure to build these conditional instances. We are enumerating all these homomorphisms from query variables to the labeled nulls in the C instances. And then we are post-processing for satisfiability and redundancy using SMT solvers once again. Yes.
Yeah, so I'm trying to understand what language you're working with. So you said domain relational calculus.
Yes.
So you have these like filters like, and then less than equal to.
Yeah, so we have all those like the atomic predicates. We are allowing like, yes.
Okay, and then
So no aggregates, no aggregates. Yeah.
very good.
Yes. So as long as the sequel can be converted to domain relational calculus with these conditions, then it is fine. Yeah. Yes, ma'am.
So I understand why you need a heuristic stopping condition, but I'm also worried that if you consider general first order logic expressions, it's not clear what the chase means.
Let me show you. Yeah, so this is not complete. Okay, we no guarantee on the completeness because of the stopping condition and also because of like when you have universal quantifier. So we are trying to get a solution that covers like you can have a stopping condition on time, you can have a stopping condition on number of variables you are adding to the conditional instance, and if you are yes. Yeah.
Are the labeled nulls invented by this chase?
Yes. Yes. They are built from scratch, from empty conditional instance. Okay, so let me do a very simple walkthrough. So you have a very simple query here. Find drinkers who either like Budweiser or do not like any beer. Okay, so we have a for all, and for all is the source of all complexities. So if we have this or at the top, so this is a recursive algorithm. We are building all this set of conditional instances one by one. If we have or, we are reducing it to these three conjunctive trees, like the both branches are true or one branch is true and the other branch is not. Let's proceed with the middle one here. This is the simple one. So this one has conjunction and they are exist. So you consider like all branches. You start with an empty mapping. So I am keeping track of the domains of all these variables that are there. And also I'm keeping track of the homomorphisms. Okay, so mapping from the query variable to our C instance variables. So first, I have D for drinker. So I am introducing a new variable D1 here. Domain of beer that is already given. So this is Budweiser. And my first homomorphism is D2, D1. Then, so I have a simple conditional instance here, like only one tuple D1 and Budweiser in the likes. Then I'm checking whether this satisfies the query. So this one could be empty. So I will check all the mappings for this new variable B. So it could come from the existing domain, or it could be a new level null. So here, if you map this beer to this existing value Budweiser, then this is true that likes and D1 Budweiser is already in the C instance. So this evaluates to true. Now I will check a new. So this is the homomorphism for this conditional instance. Okay, so I got our first conditional instance. How about the next one? Then there exists B could be a new beer B1. So I will check with that. Again, proceed here. I will add a new likes tuple D1 B1 and then check that this also satisfies the query. So I got another conditional instance. Okay, so I could either have one likes tuple or I could have two likes tuples here. For the first one, when we have this for all, that is the tricky one because now different branches could have different mappings. So what we do that we take all of them and merge all the results. And especially like if you have a disjunction below for all, then it gets real complex. Like you can see that for all px or qx, you cannot do that trick. Like you will miss some solutions that if you check both are true or one is true.
Excuse me, as you wrote the query, it is not safe because of the universal quantification. You need to say something if B is a beer. You did it implicitly when you kept track of the domain.
Yes.
But the query as written is not something.
So I think like this was like one of the roadblocks that how do we define this safety when we are doing all this chase to construct the solution. I think these in the original one we have you are right. Like sorry, this wait, what we are doing, like we are doing a mapping and then we are proceeding, but the safety was like
You must have
yes.
be from some other, from the active domain of some other relation.
Exactly. So this is like the partial tree. So this is have some bindings are coming from the top. That like you are building homomorphism, like you already have some mapping, and then you are extending for the subtrace. But you are right. So like when the safety for this problem, that was one of the, like how do we have this binding before we proceed, that was one of the bottlenecks. So this so what I'm hiding here, this exact notion of coverage and mapping. So this was quite complex, like going through the ground instance and then mapping back them to the conditional instances. And then we had some other optimizations for these complex cases for all, and then followed by a disjunction. Okay, so I will just show you that in this project, we frequently do user studies in consultation with IRB. And what here we had a pilot study with some undergraduate and graduate students. So we gave them to spot errors in two SQL queries, QA and QB. Each has two errors. So when you work with students and when you need feedback from students, you cannot do a control study, like a fully randomized control study. You cannot give half of the student one query and the other half the other query. So what we did, we randomized with the query, like half of the student got QA as the treatment and QB as the control, and the other half got QA as the control and QB as the treatment. And then we showed them the concrete values, the ground instances from our previous work and these abstract instances. So the result was sort of mixed, that we saw that ground instances, they were more comfortable in some sense, like this meaning of these conditional instances that took them some time to understand like what it means. But otherwise, when we showed them a set of conditional instances, that helped them find multiple errors, which one ground instance could not help them find. So this has promise, and we have to figure out like how to make it like more understandable to students in a more natural language form. Summary, this database education and automated TA is an important and potentially high impact area of research. It uses database theory, database systems, optimization, user interface, user study. Several groups are working on this. Wolfgang is working on some similar like this database, how to help students understand the meaning of database queries, and also groups from Georgia Tech and Singapore, like many groups are working like in this direction. What we did in this work is query characterization by conditional instances. Advantages is that it is test instance independent. We are expressing the difference between two queries, Q1 and Q2, and we are capturing different ways to satisfy a query. So as a result, this is undecidable problem, but in any case, we are giving a solution using Chase. And then we are doing this detailed user study to help users, especially students, spot the error. We are collaborating with our colleagues in computer science education, and we have several other work in this project with debugger tracer for SQL, which is much more complex than relational algebra or relational calculus, and how to generate hints to fix a query. So this is the project web page. Like these tools are all available online, and if you want to give them a try, just let me know and I can share them with you. And there are several open questions that these conditional instances, this does not work for aggregates or if you have a having clause. In the previous work for ground instance, we used the work by Val and Daniel and Yale on this provenance summary for aggregates, for handling aggregates and having. But for conditional instances, we do not know how to approach there. So this is something to study. What would be other decidable forms of explanation? Like you as an instructor or teaching assistant, what form of explanation you would like to give students, and can we capture that, can we formalize that, and can we have automated solutions to get to that? Okay. So of course we want explanations in natural language, and a big questions in this work is how to use or get around LLMs. That because you can, like, students can ask the LLM that how is highest different from non lowest, and they will probably get a good answer there. Okay, so I guess that's it, and happy to take more questions. Thank you.
We have lots of time. Fine.
So I wonder if the way there might be an alternative way to handle the universal quantifiers using duality. That is, so the chase is a procedure that kind of saturates a query or an instance, right? But those are existential positive queries, right? So if you have a universal query, have you at all speculated about saturating the negation of that query, which now would be an existential query? So I'm blissfully ignorant of safety.
Are you thinking of the non-answers here, or also for?
Yeah, well, so what you want is to construct these instances, right?
Yes.
So if you, instead of taking just simply a positive approach of what the instance is, that is how you can add these labeled tuples with labeled nulls and so on. It would, of course, mean expanding your entire understanding of the database to also talk about the non-answers, that is the tuples which are not in the database, and how the fact that they are not in the database affect the truth of the query. And it's possible that you can kind of, fiddle with a chase for the negation and saturate with negative facts. So you would work with two instances. One is the instance of the tuples in the database. One is the instance of the tuple not in the database.
Yes.
What I find interesting is, though, that you add that this still nonetheless allows you to talk about labeled nulls, and therefore allows you to go, at least in these examples, allows you to go beyond the active domain.
Yes.
Which I think is
There is no active domain.
I know, yeah. So that's remarkable. So there may be.
I think that will be interesting.
Calls a quarter-baked suggestion.
I think we need to explore ideas like that. That when we have, how do we do this missing values? Yeah, that is a good direction.
Your question about aggregates, does this include the group by clause also, or you just aggregates? What?
So for group by, you could, if you have group by, that is, you can ignore that because you can just do tuple by tuple. So like you can look at the, like, why one particular tuple appears in the answer of Q2 and the not in the answer of Q1. So, but it is basically the same thing. So the group by is like, but having is a more like fundamental.
What about
more questions for the discussion in a moment? First, do you want to set up, and then I.